I'll begin by introducing some fundamental data units, talk about the definition of throughput, explain the concept of maximum throughput, discuss the difference between throughput and bandwidth, and talk about channel capacity. Now, throughput can be measured at any layer of the system, so it can be measured at any of the OSI model layers, physical up through application. In order to measure throughput, we first need to look at some fundamental data units. Now, inside a computer, all data are represented as collections of digital switches, which are either on or off, 1 or 0. An individual digital switch is called a bit. And in networking, this fundamental unit is represented by a lowercase b, according to the IEEE 1541 standard, or by the word bit written out with a lowercase b using the IEC 80000-13 standard. A collection of 8 bits is called a byte, and that usage is standardized by IEC 80000-13. We say that a byte always has 8 bits. It is the smallest addressable unit of storage inside most computers. Most computers cannot address their individual bits. They can only address individual bytes. And sometimes they can't even address individual bytes. Sometimes it's even larger than that. But in networking, bytes are represented by an uppercase B. And this is true for both the IEC 80000-13 and IEEE 1541 standards. There is another term, however, that we see in networking. And this term originated from the fact that certain early computers in the 1950s defined bytes to have fewer than 8 bits. Thus, early data communications engineers used the term octet to refer unambiguously to groups of 8 bits. In modern standard usage, the word byte and the word octet mean exactly the same thing. But network engineers typically use the term octet, and you'll see octet written in many networking texts and networking documents. The symbol for octet is a lowercase o following the IEC 80000-13 standard. Aside from networking text, lowercase o in place of uppercase b, in other words octet in place of byte, is used in non-English speaking countries and in non-English texts, especially French texts. So you'll often see things like 1MO or 1GO, and that's simply the equivalent of 1 megabyte or 1 gigabyte. It's just mega octet or giga octet, but they mean the same thing because octets and bytes are equivalent in modern usage. So by modern standards, 1 octet is equal to 1 byte, and that's equivalent to 8 bits. If you see a French text that says 1 capital M lowercase o, that is equivalent to 1 uppercase M uppercase b, which is equivalent to 1 million octets or 1 million bytes or 8 million bits. So now that we have the fundamental unit of data, we can measure throughput. Throughput is a very simple equation. Throughput is equal to the amount of data that we transmit per unit time. So throughput is equal to data transmitted, the quantity of data transmitted, divided by whatever time unit we're using. The standard unit that we use for the numerator of this equation, so the standard unit that we use for the amount of data transmitted, is the bit. And the standard unit that we use for the amount of elapsed time is the second. So we normally measure throughput in bits per second, and we can use SI or IEC prefixes in order to give us a convenient shorthand for units of thousands or millions and so forth, bits per second or BPS. Now the maximum throughput of a networking system is the maximum rate at which data can be transmitted through a network connection at whichever layer of the OSI model that we're measuring. So if we're measuring the physical layer, the maximum throughput is the maximum rate at which we can send data through a network connection at or using that particular physical connection, using that particular physical medium. But since each layer of the OSI model adds a certain amount of protocol overhead, in other words, it transmits some extra data added on to the data that we actually would like to send, for a given maximum throughput at a lower layer, the expected maximum throughput, as we're going to see it, will be less at the layer above it. So, there is a term that is also used to describe maximum throughput, and that term is digital bandwidth. It's measured in bits per second, measured at any layer in the OSI model, and it's kind of a weasel word, because the quote-unquote bandwidth, meaning digital bandwidth, of a networking system could actually be set by a provisioning policy at the data link network or transport layer, and it might not be a physical layer of the actual transmission, a physical limitation of the actual transmission system. In order to avoid confusion, though, I'm not going to use the term digital bandwidth. I'm instead going to say maximum throughput. And in my lectures, the word bandwidth is always referring to a physical layer property, and it is always a unit that is expressed in hertz. I am using the analog signal processing definition of bandwidth. So at the physical layer, the bandwidth capacity of the physical medium does limit the maximum throughput that's physically possible. In other words, at the physical layer, the amount of analog bandwidth I have does play a role in determining the maximum amount of throughput that I can transmit through that particular physical medium. In other words, it gives me a theoretical maximum speed. And this theoretical maximum speed is called the channel capacity of the medium. And that channel capacity is given by this equation. This is the Shannon-Hartley theorem. And this says that the channel capacity of a physical medium is equal to its bandwidth in hertz times the log of 1 plus the ratio of the signal power expressed in watts divided by the noise power expressed in watts. Now, what I can see immediately from this equation is that channel capacity is directly proportional to bandwidth. So, as I increase my bandwidth, my channel capacity should increase, assuming that my signal and noise powers stay the same. If I decrease the bandwidth of a physical medium, or I switch to a physical medium that has a lower bandwidth, the channel capacity of that medium will be less than my first medium, assuming that my signal and noise powers are the same. But my signal and noise powers do play a role in this bandwidth calculation. For example, if I have an extremely high noise power, let's say I have 1,000 watts of noise power, but I only have 1 watt of signal power. This 1 plus 1 over 1,000 is still going to be close to 1, and the log of 1 is 0, which means my channel capacity is going to be 0. There's too much noise for me to transmit any data through that channel. On the flip side, if I could somehow have a noiseless channel, the limit as this denominator approaches infinity of a finite signal power over that noise power that's approaching 0 is infinity, and infinity plus 1 is still infinity. The log of infinity is infinity times whatever the bandwidth is. I would have infinite channel capacity. So if I could have 0 noise in all signal, my channel capacity could be infinite. It is a physical limitation given to us by the laws of physics for any transmission medium that we use that the noise power is not going to be 0. We are in fact going to create a certain amount of noise simply by transmitting the signal in the first place. And the reason for that is quite simple, and that's that the electrical circuits that we're using to transmit the signal themselves introduce noise. The lower the noise produced by the electrical circuit, more commonly the more expensive the circuit. So economics is going to limit us to certain ranges for this value, and ultimately our channel capacity is going to become much more dependent upon the bandwidth. So that channel capacity expresses the maximum possible throughput of a physical link, and it's directly proportional to the amount of available bandwidth. It's also related to the signal-to-noise ratio. A good or high signal-to-noise ratio does increase the capacity of the channel, while a bad or low signal-to-noise ratio decreases the capacity of the channel. And at a fixed signal power, high noise power is going to reduce the maximum throughput available to the channel. Try using an 802.11 wireless network, for example, in an apartment complex or a block of flats in British English, and you'll see that you'll never quite get the speeds that is advertised by the particular wireless networking standard. And the reason for that is that there's so much noise from everyone else's wireless devices that it reduces the maximum throughput that your wireless devices can achieve because the channel's simply too noisy. A noiseless channel, a completely noiseless channel, is physically impossible because modulation, transmission, reception, demodulation circuits all add noise. And even if we're sending data down a cable or down a fiber optic line, properties of the materials themselves introduce a certain amount of noise in the signal. Now, the component quality does affect the amount of noise that is introduced. Higher quality components, for example, will tend to introduce less noise. But higher quality components have a higher manufacturing cost, and so we have to consider the economic realities of how much noise is acceptable for a given application based upon the price of the components that we would need in order to reduce that amount of noise. So to summarize, the fundamental unit of data that we use is the bit. Bytes and octets are groups of 8 bits. In modern usage, those two units are equivalent to each other. Throughput is the amount of data that we can transmit per unit time, and fundamentally we normally use bits per second as our unit for expressing this quantity. The maximum throughput of a system is the fastest data transmission speed that can be achieved over a network link. This maximum throughput can be measured at any layer of the OSI model, but it is ultimately subject to hard physical limitations that are introduced by the physical channel capacity in the physical layer.